Firstly, let us look at the RMS value of a half-wave rectified sinusoid. The average value of a half-wave rectified sinusoid is given by voltage average equals the quantity 2 divided by pi times voltage RMS. Substituting voltage RMS equals 0.707 times voltage peak, we get voltage average equals the quantity 2 divided by pi times 0.707 times voltage peak equals 0.9 times voltage peak. The RMS value is related to the average value by voltage RMS equals the square root of voltage average squared plus voltage peak squared. Substituting voltage average equals 0.9 times voltage peak and voltage peak equals voltage peak, we get voltage RMS equals the square root of the quantity 0.9 times voltage peak squared plus the quantity voltage peak squared equals 0.995 times voltage peak. Secondly, the RMS value of a square wave swinging between 0 and voltage peak will be reviewed. The square wave can be represented as a Fourier series voltage of t equals the quantity 4 times voltage peak divided by pi times the quantity sine of omega t minus the quantity 1 divided by 3 times sine of the quantity 3 times omega t plus the quantity 1 divided by 5 times sine of the quantity 5 times omega t minus, and so on. The RMS value of a square wave is given by voltage RMS equals the square root of the quantity 4 times voltage peak divided by pi squared times the quantity 1 squared plus the quantity 1 divided by 3 squared plus the quantity 1 divided by 5 squared, and so on, equals the quantity 4 times voltage peak divided by pi times the square root of 1 divided by 3 equals 0.471 times voltage peak. Thirdly, the RMS value of a triangular wave swinging between 0 and voltage peak will be identified. The triangular wave can also be represented as a Fourier series voltage of t equals the quantity 8 times voltage peak divided by pi squared times the quantity sine of omega t minus the quantity 1 divided by 9 times sine of the quantity 3 times omega t plus the quantity 1 divided by 25 times sine of the quantity 5 times omega t minus, and so on. The RMS value of a triangular wave is given by voltage RMS equals the square root of the quantity 8 times voltage peak divided by pi squared times the quantity 1 squared plus the quantity 1 divided by 9 squared plus the quantity 1 divided by 25 squared, and so on, equals the quantity 8 times voltage peak divided by pi squared times the square root of 1 divided by 15 equals 0.327 times voltage peak. The root mean square, often abbreviated as RMS, is a statistical measure of the magnitude of a varying quantity. It is especially useful when dealing with alternating currents and voltages, as it provides a way to express the effective value of a waveform that changes over time. The RMS value is calculated by taking the square root of the mean of the squares of the instantaneous values of the waveform. For a sinusoidal waveform, the RMS value is equal to the peak value divided by the square root of 2, which is approximately 0.707. However, for non-sinusoidal waveforms such as square waves and triangular waves, the RMS value is different and must be calculated using the appropriate formula. Let's delve deeper into the calculations and concepts related to the RMS values of different waveforms. For a half-wave rectified sinusoid, the waveform is only present during one half of the cycle, while it is 0 during the other half. This means that the average value of the waveform is not 0, as it would be for a complete sinusoidal wave. The RMS value of a half-wave rectified sinusoid is approximately 0.995 times the peak voltage. This value is higher than the RMS value of a full sinusoidal wave because the waveform is only present for half of the cycle, effectively increasing the overall magnitude of the waveform. To calculate the RMS value, we first determine the average value of the rectified sinusoid, which is given by voltage average equals the quantity 2 divided by pi times voltage RMS. We substitute voltage RMS equals 0.707 times voltage peak into the equation, resulting in voltage average equals the quantity 2 divided by pi times 0.707 times voltage peak, which simplifies to voltage average equals 0.9 times voltage peak. Then, we use the relationship between the RMS value and the average value, given by voltage RMS equals the square root of voltage average squared plus voltage peak squared. we substitute voltage average equals 0.9 times voltage peak and voltage peak equals voltage peak into the equation, resulting in voltage RMS equals the square root of the quantity 0.9 times voltage peak squared plus the quantity voltage peak squared, which simplifies to voltage RMS equals 0.995 times voltage peak. Next, let's consider the RMS value of a square wave swinging between 0 and voltage peak. A square wave is a periodic waveform that alternates abruptly between two voltage levels, in this case 0 and voltage peak. The square wave can be represented as a Fourier series, which is a mathematical representation of the waveform as a sum of sinusoidal components. The Fourier series for a square wave is given by voltage of t equals the quantity 4 times voltage peak divided by pi times the quantity sine over omega t minus the quantity 1 divided by 3 times sine of the quantity 3 times omega t plus the quantity 1 divided by 5 times sine of the quantity 5 times omega t minus, and so on. The RMS value of a square wave is given by voltage RMS equals the square root of the quantity 4 times voltage peak divided by pi squared times the quantity 1 squared plus the quantity 1 divided by 3 squared plus the quantity 1 divided by 5 squared, and so on, which simplifies to voltage RMS equals the quantity 4 times voltage peak divided by pi times the square root of 1 divided by 3 equals 0.471 times voltage peak. Finally, let's examine the RMS value of a triangular wave swinging between 0 and voltage peak. A triangular wave is a periodic waveform that linearly increases and decreases between two voltage levels, in this case, 0 and voltage peak. Similar to the square wave, the triangular wave can also be represented as a Fourier series. The Fourier series for a triangular wave is given by voltage of t equals the quantity 8 times voltage peak divided by pi squared times the quantity sine over omega t minus the quantity 1 divided by 9 times sine of the quantity 3 times omega t plus the quantity 1 divided by 25 times sine of the quantity 5 times omega t minus, and so on. The RMS value of a triangular wave is given by voltage RMS equals the square root of the quantity 8 times voltage peak divided by pi squared times the quantity 1 squared plus the quantity 1 divided by 9 squared plus the quantity 1 divided by 25 squared, and so on, which simplifies to voltage RMS equals the quantity 8 times voltage peak divided by pi squared times the square root of 1 divided by 15 equals 0.327 times voltage peak. Understanding the RMS values of different waveforms is crucial in various applications, including power systems, audio engineering, and signal processing. The RMS value allows us to compare the effective power or energy delivered by different waveforms, regardless of their shape. For instance, in power systems, the RMS voltage is used to determine the amount of power delivered to a load. In audio engineering, the RMS value is used to measure the loudness of a sound signal. In signal processing, the RMS value is used to quantify the strength of a signal. Furthermore, the RMS value is essential for designing and analyzing electrical circuits. When dealing with alternating currents and voltages, the RMS value is used to calculate the average power dissipated by a resistor. The average power is given by power average equals voltage RMS squared divided by resistance, or power average equals current RMS squared times resistance. These equations are fundamental for determining the appropriate components and ratings for electrical circuits. In summary, the RMS value is a fundamental concept in electrical engineering and signal processing, providing a way to express the effective value of a varying quantity. The RMS values of different waveforms, such as half-wave rectified sinusoids, square waves, and triangular waves, can be calculated using specific formulas based on their shape. Understanding these calculations is crucial for various applications, including power systems, audio engineering, and signal processing. By using the RMS value, we can accurately compare the effective power or energy delivered by different waveforms and design appropriate electrical circuits. Now let's talk about some applications of these RMS values in practical scenarios. In power electronics, understanding the RMS voltage and current of different waveforms is crucial for designing efficient and reliable power converters. For example, In a half-wave rectifier circuit, the RMS voltage of the rectified output is lower than the RMS voltage of the input sinusoidal voltage. This means that the power delivered to the load is reduced and the efficiency of the rectifier is lower. Therefore, it is important to use a full-wave rectifier, which provides a higher RMS voltage and better efficiency. In audio systems, the RMS value of the audio signal is used to measure the loudness of the sound. The higher the RMS value, the louder the sound. Audio amplifiers are designed to deliver a certain amount of RMS power to the speakers. If the amplifier is overloaded, it can clip the audio signal, resulting in distortion and a lower RMS value. Therefore, it is important to choose an amplifier that can deliver enough RMS power for the desired loudness level. In instrumentation and measurement, the RMS value is used to measure the true value of an alternating current or voltage. Traditional meters often measure the average value of the waveform, which is not the same as the RMS value. The RMS value provides a more accurate representation of the effective value of the waveform, especially for non-sinusoidal waveforms. True RMS meters are designed to measure the RMS value of any waveform, regardless of its shape. These meters are essential for accurate measurements in various applications. In motor control, the RMS current of the motor windings is used to determine the torque produced by the motor. The higher the RMS current, the higher the torque. Motor drives are designed to control the RMS current of the motor windings, allowing for precise control of the motor's speed and torque. Understanding the RMS values of different waveforms is also important for safety considerations. High RMS voltages and currents can be dangerous and can cause electric shock or fire. It is important to use appropriate safety precautions when working with electrical circuits and equipment. For example, it is important to use insulated tools and wear appropriate personal protective equipment. In addition to the applications mentioned above, the RMS value is also used in various other fields, such as telecommunications, medical imaging, and radar systems. In telecommunications, the RMS value is used to measure the power of radio signals. In medical imaging, the RMS value is used to measure the intensity of ultrasound waves. In radar systems, the RMS value is used to measure the strength of radar signals. The ability to accurately calculate and interpret RMS values is therefore an essential skill for engineers and technicians in a wide range of disciplines. Now, let's discuss the relationship between RMS value and power calculations in more detail. The instantaneous power dissipated by a resistor is given by power instantaneous equals voltage instantaneous times current instantaneous. However, for alternating currents and voltages, the instantaneous power varies over time. The average power dissipated by a resistor is given by power average equals 1 divided by time period times the integral of power instantaneous over one time period. Using the RMS values of voltage and current, the average power can be calculated as power average equals voltage RMS times current RMS. This equation is fundamental for calculating the power dissipated by any load, regardless of the waveform. In addition to resistors, the RMS value is also used to calculate the power consumed by other types of loads, such as capacitors and inductors. However, for these types of loads, the power consumption is more complex and depends on the phase relationship between the voltage and current. The power factor is a measure of the phase relationship between the voltage and current. A power factor of 1 indicates that the voltage and current are in phase, and the power consumption is maximized. A power factor of 0 indicates that the voltage and current are 90 degrees out of phase, and the power consumption is 0. Capacitors and inductors have power factors that are less than 1, which means that they consume less power than resistors for the same RMS voltage and current. Understanding the RMS value and power factor is essential for designing efficient and reliable electrical systems. Power companies often charge customers based on their power consumption and power factor. Customers with low power factors may be charged higher rates to compensate for the increased losses in the power grid. Power factor correction is a technique used to improve the power factor of a load, reducing the losses in the power grid and lowering the customer's electricity bill. In conclusion, the RMS value is a versatile and essential concept in electrical engineering and signal processing. It provides a way to express the effective value of a varying quantity, regardless of its shape. The RMS value is used in a wide range of applications, including power systems, audio engineering, instrumentation and measurement, motor control, and telecommunications. Understanding the RMS value and its relationship to power calculations is crucial for designing efficient and reliable electrical systems.